Hello, good afternoon, everyone. Well, today we are celebrating because it is the 10th episode of our sCO2 webinar series organized by ETN Global and particularly the sCO2 working group. Today we will talk about energy storage and sCO2. So for those who don't know us yet, this is who we are, ETN Global. ETN stands for Energy and Turbomachinery Network. And we are an international non-profit membership organization and strategic platform that covers the whole value chain of the turbomachinery industry. And you see some numbers. As you can see, we have more than 140 member organizations from 21 countries and 4 continents. And this is who we are, your webinar moderators. So my name is Jitka Špolcová. I work for ETN Global as a project officer. Amgat?
Yes, my name is Amgat. I'm a PhD. I started at the University of Seville. My thesis is about supercritical CO2 power cycles, marketing and commercialization. And now I'm doing my last year of the PhD working at ETN. I just started, and it goes for a year. And Marco Ruggiero is also here today.
Yeah, thanks, Marco Ruggiero, Baker Hughes. I'm co-chairing this working group. I've been doing that since the very beginning. So happy to be here and moderating the Q&A panel at the end of the webinar.
Thank you very much. Before we start, there is a few things I want to tell you. As always, they're not very entertaining, but we have to go through them. This webinar is recorded. It's also because you will receive the recording, so it's very good. You have probably noticed that you entered the room with your cameras and mics off. However, I will enable them at the end during the Q&A session that Marco just mentioned. Well, speaking about which questions, we definitely want to hear your questions. We are very interested in knowing what you think and what you want to ask. This is not supposed to be one-way communication. It is supposed to be an interactive session. So please prepare your questions. You have essentially 2 ways to ask them. You can either put them in writing in the chat. You can do this during presentations. Preferably, please write who your question is for. And this person will answer your question also in writing in case the answer is pretty straightforward and it's quite short. If it's longer and more complicated, we will take it to the end. So we will take your questions during the Q&A session, at which moment you will also have the opportunity to ask questions orally as opposed to writing them. So it's entirely up to you how you want to do it, but we really are interested in you asking your questions. Your phones, please have them ready because we will have Slido questions as we always have. So you will need your phone pretty soon. And the last icon shows that you don't need to take many notes from the presentations unless you really want to, because we will share the presentations with you after the end of this webinar. So these are the people that will keep you company today. We have 3 speakers. You know who they are because we shared them. We shared their names before at the website and also in my email. We have Isabel, Stefano, and Tim. They will be introduced in more details just before their presentations. So we are almost done with the introduction, but before we go to presentations, we have the announced Slido question. So this is your connection slide. So please scan the QR code. And once you are done, I will leave the floor to my colleague Amgat, who will introduce the first Slido question.
You still have the QR code up to the left if you didn't scan it in the last page. And the question would be, why do you think energy storage should be relevant? Try to write 2-3 words, not to make it too long. That why you think it I see. Looking at these answers, it's clear we all recognize the fundamental challenge of energy transition. Renewables are intermittent, but the demand is relatively constant. Many of you mentioned balancing and maybe, yeah, it's about the balancing. The storage allows us to decouple when we generate energy from when we use it. It turns the variable energy into dispatchable one, giving power on demand. I mean, there is also a strong economic element. Storage help avoid curtailment, which is essential. It's like throwing energy away when it's extra. If there is high solar day and there is excess in solar, this would be very useful to store it. It could be used during night hours or non-solar time, even during the day. It also defers the need for expensive new power lines by managing local congestion. Yeah, very good answers. It's all on the point. Not to take without any further ado, we go ahead and introduce our first speaker.
Thank you, Amgad, for debriefing. So I'll stop sharing my screen while the first speaker is getting ready. The first speaker is Isabel Gonzalez, who is a scientific policy officer at the Joint Research Center of the European Commission. With a background as an industrial engineer and a Master of Science in thermal energy systems, she has gained 20 years of experience across various energy domains. Currently, she focuses on energy efficiency products, demand response, and exploring flexibility solutions. Isabel is also in the core team developing the European Energy Storage Inventory, a platform showcasing energy storage projects across Europe. I suspect that this is exactly what Isabel is going to talk about. So please, Isabel, the floor is yours.
Thank you so much. Thank you for this organization and for this opportunity to present the inventory. So as Ditka said, I work for the Joint Research Center of the European Commission, in particular in Unit C3. This is the content of my presentation today. I'm starting with some generic background, the GRC, and then I will deep a bit on our European energy inventory, with a description of the data, the description of the platform, and main results that we had. And further information if you are interested in further discussions. So the GRC is a DG of the European Commission, one of the institutions of the European Union, and the role is providing scientific evidence to support the policies. And there are three main pillars to do that: anticipate the integration and impact of our research. In this sense, the GRC is also linked to several research facilities across Europe. My unit is also split in three sites, actually, in Petten, in the Netherlands, in Ispra, in Italy, and where I am based in Seville, in Spain. And our unit received this endeavor of having this platform from DG Ener, because we are working on several aspects of the grid, like how to integrate renewables in the grid, enable flexibility, distribution system, a lot of aspects in market design and prices. And also we have a couple of laboratories, one in Petten, more dedicated in smart homes, and one in Isbran, more dedicated for smart grids and electrical vehicles integrations. To achieve this platform, we are working with DG Ener and also with other units, also for inside the GRC, dedicated to other aspects like raw materials or identifying other ways to present information. And as you said, for the first question of Slido, storage is a crucial topic. Currently, it enables the integration of renewable deployment. There is also an ongoing exercise in Europe to identify the flexibility needs for every member state. And storage, as you can imagine, is a key for this flexibility. And also it supports the security of supply, avoiding curtailments and making more resilient our grids. So with this background, we started looking at how to identify the energy storage facilities, and we detected that there were several classifications of technologies present in the literature. So we made an effort to identify which were the main classifications, and we achieved this scheme that you see in this slide. We have mechanical, we have electrochemical, electrical, not very in operational or commercial mode, but still there, chemical and thermal. For mechanical, for instance, the main one, the main operational one is pumped storage hydropower, but there are new technologies like compressed air energy storage, quite relevant for today, and also flywheels, for instance. You see for electrochemical, which means batteries, there are a lot of different technologies present already in the market. The main one is lithium-based batteries, but there are also other technologies, and you can find also other solutions. For chemical, although there are several types, in our inventory, we just mapped the facilities based on hydrogen. And for thermal storage, you will find also in our platform several types of solutions and sub-technologies. Once we identified all the technologies, also we wanted to identify the several status, the life cycle of a project, because we didn't want just to look at the operational project, because as I said, it is a crucial moment for storage. So there are a pipeline of hundreds of projects in other status, like announced or permitted, or even under construction. Also thanks to all the actions that the member states have launched in the recent years. So we looked at the different data providers, and at the end we selected Wood Mackenzie as our main data provider, but also we combined this source with other public sources, with some projects from the International Energy Agency, and also we are taking directly some data of facilities from owners. Once we have everything, we improve our data, we complement the fields missing, and also we make some of our fields available to the public. And it is noticed in the box on the right. You can check for every facility the technology, the status, the power and capacity, and the country and the region. Actually, when we made this platform, we didn't want just to look at the member states of the European Union, and we have included also other neighborhoods like United Kingdom, which is also super relevant in terms of storage deployment. You see, for the time being, our main data are for power and not for capacity, because when we checked all the sources, there were big difference and gaps in capacity, in energy terms. So for the time being, our platform is based on power, but we're working on improving this aspect. So here, this is the link of our platform. And as you see on the slide, there are two main sections. On the left, you have the dashboard, and on the right, you have the interactive map. For both sections, you can filter, you can adapt, and everything is adapting to your selection and to your interest. Let me stop a moment the presentation, because I wanted to show you directly the platform. So here, as I said, this is the link of the platform. It takes a bit to upload all the dashboard. Then when you have already in your screen, you can see a figure about the status of projects, a figure about the countries, the number of projects, and by technology, also the same global data in terms of main technologies. The dashboard can be selected for any of these parameters. You can select clicking on one of the parameters, like for instance, I can select operational, and all the dashboard adapts to my selection. Also, you can combine several issues like operational for France, Italy, and Spain, and you have the figures and all the numbers adapted to your selection. If you can't find something here very at a glance, you can also go to the details selections there on the top. So for instance, you can clear all the selection previously adapted, and maybe you can just have a look at the, I don't know, pumped hydro, for instance. So here you have all the names about pumped hydro in Europe. So this is the section of the dashboard to have total numbers, but also you have at the bottom a map. Also, you can reach the map here, selecting interactive map. And here you see all the dots for all the facilities across Europe. Depending on the color, you see one technology or another. And you can also filter. Like, for instance, you can filter by electrochemical search. And like that, you see only in blue, and you see all over Europe, all the projects. But maybe you can also want to have a look at a status. For instance, you can again combine several filters. You see operational batteries in Europe, and here it is the map. Also, you can filter about capacity or about amount of power. You see, it is totally adaptable to your selections. And if you click on a particular project, you can have, for instance, here, you can have some details about that project. And actually, you have a dedicated website or page with all the information about one project. For instance, it is an operational battery, nickel manganese cobalt oxide battery. And here it is the power, the capacity, the coordinates. You can find all the information. Let me come back again to the presentation. So, for instance, this dashboard, well, it's like a game. You see, you can play. And in this one, I selected 3 countries. The expectations, which means the project's not operational and not cancelled, It's just announced, permitted, or under construction. And you see also for the technology of electrochemical. So depending on the color, you have the announced, the permitted, or under construction, and for the 3 countries selected. And here, for instance, I made another selection. I took from 100 to 150 megawatts. And you see all the different technologies, not for chemical, because for hydrogen, we have smaller projects. But you see across Europe, different technologies. For instance, it's quite relevant when you see, when you look at Spain, you can detect more thermal projects, and there are a lot of molten salt linked to the concentrated solar power. And here, as I mentioned before, there is a page with all the information from one project. So apart from the website itself, we have developed several reports, and this one we published in November. You can have there the link in the slide to get to the presentation. Also, it is available on our website. We are about to publish another one looking at the different member states plans, and not only the energy and climate change plans, but also for DSOs and TSO plans. And in this report, we have analyzed, for instance, the main values. And as you can see here in a second, the expectations are higher than the operational power in Europe. And the main technology is supposed to be installed is batteries. Also by country, you see there are a lot of differences in terms of how the different countries have supported schemes, and there are also some market aspects introduced in the report. For instance, here you see United Kingdom is the main one in terms of operational power, but also in terms of expectations. But there are relevant countries like Germany or Spain or Italy with a lot of efforts also. They have also put some objectives in their plans. And so here you can compare. You can look at one of the countries and see if you think there are market aspects to consider, that their ancillary service can be remunerated or not. And also, for instance, you see if there are capacity markets for those countries. So you can have an idea of the drivers and the bottlenecks for every member state or country considered in our platform. And just this last slide of my presentation, but I wanted to give you an idea about this is the dashboard and a platform in real time, which means that last update for it was a couple of weeks ago, but we are updating the information constantly. In the official launch of the website, it was March last year, and we started like with 1,800 projects, and nowadays we have like 3,500. So you see there are a lot of movements just in Europe countries related to storage facilities. The main technology is electrochemical in terms of increasing numbers, And it's also the reason we have improved our data, and we have incorporated new sub-technologies to identify the different aspects of the main categories. And we have also put dedicated pages to look at some of the projects. As I said, we are also developing other reports in the framework of this collaboration with DG Ener. There are a lot of policies identified in the main report already published in November, where you can also look at the main regulations and policies from the European Union to promote or support schemes facilitating the storage deployment. Regarding our data, we are still improving and completing data. As I said before, for instance, we are now trying to get the capacity data in terms of energy for all the projects. And also we use an API to get the data directly from the data providers. And we process and consolidate all the data. Also, we have improved, especially for some gaps detected at the beginning of the project. For instance, the thermal projects were not, we didn't find a good source at the beginning, and also for some countries, because there are several public sources where you can check at a country level. And finally, we are trying to put new functionalities in the dashboard and in the website. For instance, we are now incorporating an historical figure. It will be ready soon. As we started last year, it doesn't have a lot of sense to have an historical if you don't have something to compare. So at the end, we are starting now to look at the historical evolution of the deployment. And also the last messages that I wanted to show you is that we are also collecting data directly from owners. I already mentioned at the beginning as one of our sources. And you see, maybe you know some facilities, or you are even the owners. So please, we have a template in our website, and you can use it to provide your own data. It's a way to check if your projects are there. It's another way also to promote your projects. And we wanted to promote the storage, energy storage in general. So if you want to be part on a data source, on a data set from the European Commission, it's your opportunity now to contact us, fill in the template, and send us to our mailbox. And that's all from our side. You will have there my email and my colleague Marcello, who is the leader of this project, and I'm happy to answer your question and after with the Q&A. Thank you.
Thank you, Isabel. It was really informative, and the tool is great. I think it's very useful for researchers, public and private entities, or even students. So thank you. Now we have Stefano Barberis. Stefano received his PhD in turbomachinery and advanced energy systems engineering at the University of Genoa. He's also a senior mechanical engineer with expertise in a number of areas, including renewable energy sources, techno-economical feasibility studies, research activities on energy storage, hydrogen and renewable energy systems, and project management. He is currently appointed as a researcher and assistant professor at the University of Genoa in the Turbomechanical Power Group. At the same time, he coordinates the scoop test project. Please, Stefano, the floor is yours.
Okay, good afternoon, everyone. Sorry, I was thinking that I was not muted. So Good afternoon, everyone, and thanks also to ETN for this opportunity. As I said, I am going here today to present briefly the sCO2 project. That is a project that I'm personally coordinated and whose goal is mostly to validate an innovative supercritical CO2-based thermally integrated pumped thermal energy storage. The goal of this project is indeed to realize a first of its kind laboratory of this supercritical CO2 double loop with a heat pump charging cycle and a power cycle as discharging cycle, and operate it, enabling also the potential valorization of industrial waste heat and waste heat coming from, for example, power plants, also to facilitate the facilitate flexibility of a combined cycle, for example, and as well as the increase of the round trip efficiency of this type of storage. We already mentioned it in the previous speech, the importance of long duration energy storage and let's say of energy storage of 360 degrees. But in this moment, if we look at European energy system, but I would like to say more or less also US based one, we always need to energy storage to solve two problems. From one side, long periods with small renewable production, and from the other side, short-term changes either in power supply or needs of demand. Indeed, you know, if we look at what we call the curve, we need more and more energy storages that should store energy during this part of the day, and then energy storage with a large power capacity that's also able to actively operate and rapidly ramp up to provide back power to the grid. So said that, we have to think about energy storage that have a rotating machine also in order to offer grid flexibility services that are needed due to the intermittent presence of renewable. It's also important to say that if we look at energy, actually energy can be required and will be required in the form of heat as well as electricity in the next decades. So storing electricity via power to heat to power solution and storing electricity via thermal energy storage media could have some benefits also because it could enable us to provide heat to some users. So saying that, going towards a more sustainable energy system with more and more energy sources and more electrified processes, it will become more and more possible and more needed to have, as I mentioned earlier, large-scale energy storage, but also in terms of both energy capacity as well as in terms of power capacity to, cover the peak of demand as well as to, potentially start to think about the weekly shifting of energy from production period to demand period. And to do that, if we would like to work more on daily, weekly, at least level, we cannot rely only on, as we said, batteries or electrochemical storage, but let's say thermomechanical storages could be an option more than other type of solutions like power to hydrogen that has more a seasonal effect, mostly because in that case this thermomechanical storage can offer grid flexibility services, and they can also, as I mentioned, give the possibility to dispatch thermal energy and not only electric energy one. In this sense, promoting Carnot battery and promoting power to heat to power system is becoming more and more important in order to offer grid services whose target in terms of power capacity could be something around 10 megawatt, and the discharge time, so in terms of energy capacity, has to be something between 4 and 10 hours. So let's say we have to think that also according to the previous slide, power to heat to power system should offer the type of services that currently are offered by pumped hydro, but let's say with maybe a shorter term in terms of energy storage capacity. But so this is something that the possibility to use Carnot batteries and power to heat to power system at this purpose is something that has been widely investigated. But let's say when we look at Carnot batteries, we mostly, recognize two limits. The first limit is the fact that when we look at a power-to-heat to power system, we deal with complex energy system with different type of components, so with high capex in this sense, and we, particularly if we look at storages that have a limited number of hours along the whole year, if we would like to have competitive levelized cost of storage, we must reduce the number of the components. And, you know, due to the double cycle in terms of charging and discharging, and particularly when we look at a discharging cycle with low temperature thermal energy storage, at the end of the day, Carnot battery have limits on round trip efficiency. So we have to try to increase the round trip efficiency, and we have to try, maybe if possible, decouple charging and discharging cycle, maybe looking at the possibility to exploit externally available heat sources that could come from thermal renewable or waste heat. Integrating indeed this type of freely available heat sources could facilitate us to increase the COP of our charging cycle, of our high temperature heat pump, and therefore whatever will be the discharging cycle efficiency, increase as much as possible the RTE. So why we are looking at the possibility to use supercritical CO2 in this sense? We are looking at the possibility to use supercritical CO2 in this sense because at the end of the day, particularly if we look at freely available heat sources like, as I said, industrial waste heat or, renewable thermal, supercritical CO2 can offer good flexibility, good, let's say, efficiency value, both in a power cycle, so discharging cycle, as well as charging cycle, high temperature heat pump, also enabling us, particularly if we look at high temperature heat pump, to operate and such heat pump at higher temperature than the traditional refrigerant. So enabling us to store heat at temperature that could be 300, 350, 500 degrees C. In this sense, we would like to do that in scoop test, promoting the possibility to set up a waste heat-driven pumped thermal energy storage enabled by supercritical CO2 components. This is something that we will do via, as I mentioned, the thermal integrated pumped thermal energy storage, where our heat source is used as heat sink for a heat pump, thus increasing the COP of the heat pump, and then in a second parallel cycle, discharge our thermal energy storage, able to store heat at relevant temperature with good efficiency. The idea, therefore, is to develop and validate this supercritical CO2 pumped thermal energy storage to be potentially integrated in industrial sites or power plants, also to make, for example, the latest one more flexible. The idea is that the main goal of the project is to integrate and realize this laboratory prototype into University of Genoa laboratory hosted by Tirreno Power. Initially, indeed, Tirreno Power is a combined cycle power plant, 800 megawatt, located in Vado Ligure, so close to Genova. And initially, the idea was to, exploit directly some waste heat coming from, for example, the sparging steam or the auxiliary boiler steam of the bottoming cycle of this combined cycle. I said initially because at the end of the day, now we are, in the second, or more or less in the second phase of the project, because the project started in November 2023. We understood that it could have been more practical and also feasible from a cost effectiveness point of view, emulate these waste heat sources via an electric heater based on real power plant data. So in principle, the idea of our supercritical CO2 thermal integrated pumped thermal energy storage is and is going to be put in reality thanks to the support of industrial partner of the project, mostly realizing, as I said, two cycles. One that is the charging cycle, the dashed one, that is a heat pump where we do have a hot compressor that compressed and pump up supercritical CO2 flow at 240 degrees up to 350 degrees. Then this hot supercritical CO2 is stored. Let's say, actually, it provides heat to a molten salt loop that then provides heat to a thermocline thermal energy storage tank. And then the supercritical CO2 is expanding in a bladeless turbine, closing the loop of the charging cycle. In parallel, this charging cycle is composed by some volumetric compressor that we are, let's say, adapting from off-the-shelf refrigeration components, a recuperator provided by Alfa Laval, and then we go up to the thermal energy storage to release the heat and let's say take advantage of the heat released by the thermal energy storage to then expand the supercritical CO2 in the turbine and close the cycle thanks to a cooler. So the main objectives of the project are mostly related to validate these technologies, the single prototypes, as well as to validate the cycle as a whole, the pumped thermal energy storage as a whole, in order to drive, and thanks to the most validation test campaign, also some replication studies and the assessment of the economic safety and environmental viability of this concept. To do so, we have different partners involved from both the academic sector like Politecnico di Milano, University of Birmingham, Cardiff, and so on, as well as our KTH, as well as technology manufacturer like, for example, Enoja, who is going to realize the hot machines, the supercritical CO2 hot machines of this cycle, as well as Alfa Laval, for example, for the supercritical CO2 heat exchanger. We do also integrate in our team energy utilities like ADP or Heron that are going to study the future applicability of the concept. As I mentioned earlier, we are now more or less in the middle of our journey. So we have some relevant results. For example, the first 2 years has been quite intensive for what it concerns modeling, with iterative modeling also to define the thermodynamic envelope and the thermodynamic operating points of the 2 cycles, targeting a maximization of the RTE. Actually, we are going to RTE that is between 20 and 30% at the end of the day for this cycle at laboratory scale. But it's true that if we would be able, particularly for upscale solution, to increase the efficiency of the different machine, think about the turbine or the volumetric compressor, as well as we will be able to increase also the temperature of the storage, most probably this RTE efficiency, as we already checked with some simulation, can achieve around 0.5, 0.6. We also fully studied the design modeling of this, we performed not only the design modeling of this cycle, but also the full of design, also to drive the dynamic modeling and the control strategy development. And I put here some interesting and quite complete publications in this sense. Indeed, we studied the off-design not only looking at the part load of the charging and discharging cycle, that is something quite important for a storage, but also, for example, the impact that the variability of the thermal energy storage temperature and the waste heat temperature could have on the performance of the cycles. If we look at the work package 2, the machine, the machine work package, let's say, where we are developing the machine themselves, for what it concerns what we call cold machines, so the compressor of the discharging cycle and the turbine of the charging cycle. These machines will be delivered by SIT Technologies. And for the first one, we are readapting, as I said, off-the-shelf volumetric machines typically used in refrigeration, while for the turbine, we are currently developing and testing a bladeless expander with a nominal capacity between 10 and 15 kilowatt. In parallel, Enoja is developing supercritical CO2 machines for, let's say, hot compressor and hot turbine. And, at this point of view, these machines have been fully, let's say, modeled and designed from, rotor dynamic, fluid dynamic, and also the skid design. While for the cold machine, we are currently, characterizing them, as I said, in order to adapt these CO2 refrigeration machines to supercritical CO2 proposed. For what it concerns the thermal energy storage, we are dealing, as I mentioned, with a thermocline solid media tank that is connected with the supercritical CO2 cycle via a molten salt loop. And let's say the thermal energy storage has been fully modeled via CFD and FEM, having the chance to study the behavior, the dynamic behavior of the test itself. And at the same time, it's important to say that we have closed in the end of December the full engineering phase of the project, having the full engineering of both the supercritical CO2 loops as well as of the molten salt loop. Also, in both cases, driving, let's say, such designs via specific health and safety and risk assessment, considering the important pressure that we are dealing with, because particularly if we look at the supercritical CO2, the minimum pressure is never below 80 bar, and the maximum pressure of the particularly of the charging cycle is around 200 bar. So what will be the next steps of our project? We are going to finalize the characterization of the cold machine, also to, drive and validate the dynamic modeling, as well as we are expecting the characterization of the hot machine, thanks to the fact of the prototypes by the Noja for the same purpose. We hope that the machines and all the prototypes for the thermocline test, for the heat exchanger, and for the hot machines will be realized within the end of the year in order to integrate and commission the laboratory within the end of this year. The idea indeed is to dedicate 2027 fully to laboratory campaign. We are also working on investigation of alternative layouts, for example, integrating instead of industrial waste heat, other type of freely available heat sources, for example, high temperature solar input from concentrated solar power, but we are also trying to understand which could be the best dispatchment analysis in the different European energy markets. We already performed some publication in this sense, but we are further developing this idea, integrating in the dispatchment analysis also the flexibility market. And, last but not least, according to the final design of the machine, we will also able to perform the first full environmental impact assessment via LCA, thanks to the colleagues of CERT. So this is an overview of the goal of the project and where we are now. I really, foster all of you to follow us on our website as well as on our LinkedIn account. Thanks a lot for your time.
Oh, thank you very much, Stefano, for sharing your knowledge, expertise, and for shedding some light on the scoop test project. I think that was a very, very nice and very informative presentation. I hope that you will receive many questions, because I think that the presentation asked for them. So I would like to encourage everyone who has a question, either write it in the chat or keep it for the end, for the Q&A session that will be moderated by Marco at the end of the whole webinar. Well, now is the time to progress and to proceed with the last speaker, which is Tim Help, who is the Chief Technology Officer at Echogen Power Systems, where he's responsible for development, maturation, and transition to product of sCO2 power cycles and energy storage systems. Prior to joining Echogen in 2008, he was with GE Aviation for 13 years, where he held leadership positions in several combustor design and fuel technology teams. He received a Bachelor of Science in Aeronautical and Astronautical Engineering from Purdue University in 1987, and a PhD in Mechanical and Aerospace Engineering from Princeton University in 1993. He has published several technical journal articles and book chapters and holds 51 US patents.
So thank you for that.
Now, Tom, the floor is yours. Thank you.
All right, thank you. Good morning and good afternoon to all of you. Appreciate the opportunity to come here and speak about long-duration energy storage using supercritical CO2. First of all, thank you to Stefano for giving the presentation before mine, because he covers a pretty good level of detail on what pumped thermal energy storage is and some of the motivation behind long-duration energy storage in general. So I will I'll touch briefly on those topics, but particularly looking at where what we're doing does differ somewhat from the approach that the scoop test team is taking. So get over to the right screen. So quick disclaimer, we've been blessed with a number of U.S. Department of Energy programs over the last 5 or 6 years on this topic. So again, acknowledgement of those. We are currently working on 2 projects that are also DOE funded that are included here. For those of you who don't know who Echogen is, we've been around since 2007. Our mission in life has been the development and commercialization of supercritical CO2 based systems. So we started out in the world of waste heat recovery and primary power cycles. So basically taking heat and converting it to electricity. We've progressed as far as a multi-megawatt demonstration system shown in the bottom right-hand corner. This is an 8-megawatt machine that we built and tested at the time Dresser-Rand facilities in New York State. That's formed the basis of much of our technology development since then. We have been working in the world of industrial heating as well, high-temperature heat pumps, which from a practical perspective, are essentially a heat engine running in reverse. And then the combination of the two. And again, Stefano did a nice job of sort of laying out what the big broad perspective of pumped thermal energy storage is, where we use a heat pump to charge a thermal reservoir and then discharge it later through a power cycle to store electricity in the form of thermal. Broad strokes, pumped thermal energy storage. Interestingly enough, in Isabella's inventory, it doesn't fall neatly into a single category. It is a hybrid of a thermal energy storage technology, but with a mechanical component to it as well. But truth be told, adiabatic case and liquid air energy storage also combine those 2 aspects of energy storage. So I like to propose another category called thermomechanical. The intent here is to develop a low-cost, long-duration energy storage system that has a number of key characteristics that include, cost effectiveness as at top of mind, life, and sustainability. Our licensed partner in this is Westinghouse Electric Company. So we've been working with Westinghouse for probably close to 10 to 12 years now on power cycles, but then morphed into working with them on long duration energy storage, and to the point where we recently signed a non-exclusive license agreement with Westinghouse to deploy this technology. So when we think about an energy storage system, you'll notice cost and safety are the top two categories. Those really are the things that drive whether or not a technology will be able to penetrate this market. If you look at the economics of energy storage systems, what are the revenue streams? What are the potential, we'll just put it crassly, the money-making opportunities for installing energy storage systems? It really does come down to low cost, and of course, safety has to be at the top of the list as well. Efficiency is important, but actually less important than cost. There is a balance between the two. So when we do our design work, we always keep in mind that balance between cost and efficiency. Flexibility, the ability to install a unit like this anywhere in the globe, so we're not geographically limited like pumped hydro or underground storage systems like CASE. Stefano mentioned grid stability, the fact that these are mechanical, rotating equipment designs, so they provide inertia and VAR support that inverter-based resources really can't. Environmental characteristics are obviously important, as well as the material usage, so not using critical materials in the energy storage system. So Stefano did a nice job of, kind of walking through what these cycles are. I'm going to point out a couple of differences here. First of all, the SCO2 test is really looking at thermal integration of heat sources. This is not that. This is a truly standalone energy storage system. So we have to carry both a low temperature and a high temperature reservoir, and we are shuttling thermal energy between the two. So kind of walking briefly through the charging cycle, we have a low temperature thermal reservoir from which we extract heat. We have some amount of internal heating as well, using a recuperator, and then this hot compressor. And again, walking through the cycle here on the right, you see the same kinds of, you see the same basic pattern here. Our high temperature, interestingly enough, is very similar to the one that Stefano is using, around 350 Celsius. we extract heat from actually 2 thermal reservoirs in series, and the reason why we do that is to take advantage of the variable heat capacity of CO2 as a function of temperature. And so by splitting the thermal reservoirs this way, we can more closely match the temperature and heat transfer characteristics of CO2 across a very wide temperature range. And so we're actually storing thermal energy from 335 Celsius all the way down to 20 Celsius. And we can do that by splitting these thermal reservoirs into 2. And then what we call a low temperature expander, basically extracting some amount of some amount of enthalpy and collecting some minor amount of work from the cycle, and then closing the cycle in the low temperature reservoir. The generating cycle is in the opposite direction, but every piece of equipment basically has an analog in the charging cycle. You'll notice a couple of ambient heat rejection systems. Sorry about that. Anything that you do thermodynamically that's not perfect means you have extra heat left over. Thermal reservoir balancing is a key characteristic of a coupled thermal pump thermal energy storage system. What Stefano was talking about was a discoupled or decoupled system where the low temperature reservoir is essentially not a closed system. Here we are a closed system, so we have to manage that thermal balance. Component-wise, this is well, first of all, this artwork is for a notional 1 gigawatt-hour plant, so roughly 100 megawatts, 10 to 12 hours worth of storage. It's also very similar to the one that we're currently designing for a project I'll describe later, where it's 50 megawatts and 24 hours worth of storage. So the reservoirs are about the same physical size. I'll talk a little bit more about those in subsequent slides, but we basically have the 2 high temperature reservoirs, or one which is a packed bed thermal reservoir, similar to what Stefano looked at, but we're using heat transfer fluid as rather than molten salt. It gives us a wider temperature range to work with. A pressurized water, medium temperature, or HTR2 in the other slide. And then finally, we're working with the world's cheapest phase change material in the low temperature end, which is an ice-water mixture. Other key components, heat exchangers, which are largely of the printed circuit heat exchanger type, other than the heat rejection heat exchangers, which are traditional fin fan units, and then some 2 large pieces of turbo machinery. So a multi-stage axial power turbine. I'll talk a little bit about what the charging compressors are, and then the auxiliary rotating equipment, or the smaller cold and low temperature expander and pump. I do actually want to back up one slide real quick. Point of order here, we're not actually a supercritical cycle, we're a transcritical cycle. So we are definitively in the subcritical pressure on the low temperature end of this. And the reason why we can do that is because we're using ice water as our low temperature thermal reservoir. So we're straddling 0 Celsius here as we're adding and removing heat from the low temperature thermal reservoir. The power turbine is going to be roughly a 62 megawatt machine. It is a multi-stage axial. We're working with a couple of different OEMs. We're hoping to get that narrowed down to a single one very soon. These are basically derivatives of high pressure steam turbines. Relatively limited number of stages because our pressure ratio is lower. For this cycle, it's about a pressure ratio of 8. And again, we're driving asynchronous generators. So from the grid's perspective, this is a load they're used to, or a generating source that they're used to. Same thing on the compression side. We expect that certainly for the initial deployments, we're going to be using multiple centrifugal compressors in parallel. I did want to point out, and I saw Jungseek was on the attendee list. So shout out to the University of Notre Dame and the University of Cincinnati, who are our partners in this project, which we're basically looking at these very large scale grids, grid scale energy storage systems where we need more than 100 megawatts worth of compression to charge the system. And at those scales, you're starting to look at axial compressors as being a distinct possibility rather than individual centrifugals. So this was a DOE-funded project that we finished a couple of years ago. We actually got to the point of doing a 3-stage axial compressor test. To our knowledge, it's the first of its type. Also, we're able to exceed 90% isentropic efficiency at a range of powers and pressure ratios. So again, very successful program. We are talking to some of the OEMs about commercializing this technology, but either centrifugal or axial, we believe have a very strong technical case. When we talk about the thermal reservoirs, on the high temperature end, this is a packed bed. This is using a unique, very proprietary fill that Westinghouse has developed over the last 6 or 7 years. It has a very high heat capacity, and it also is a mechanical shape that has a self-organizing feature. You get very high packing densities under what are called random jammed packing conditions. So we want to have as much fill as possible with as limited amount of voids. That reduces the cost of the heat transfer fluid, which is really the big cost item on this. So we've been running tests here at our laboratory. This is some of the data transiently. Again, comparing the model to the data, we're highly confident in our ability to deliver a thermal reservoir system that meets our requirements. On the low temperature side, we actually are developing that here as well. We're using a supercooled water heat exchanger to drop liquid water down to roughly -2°C and then convert that into an ice water slurry. It's a very low cost way to make a very large quantity of ice. We finished our lab scale testing again, that was partially with DOE funding last year. Looked at a variety of different heat exchanger technologies and have been able to obtain reliable supercooling without spontaneous freezing. And we are scaling that testing up this year. So that's kind of the background on the technical side. Commercially, we are currently at the in between budget period 1 and budget period 2 of a partially federally funded program to develop a 1.2 gigawatt-hour system for utility in central Alaska. It's a very interesting place to do technical work, very harsh climate, but they are in a very unusual grid situation, very small grid with some limited ties to other utilities in the area, and they have some strong needs to limit the amount of peaker generation that they're using. And so this has been, again, an ongoing project. We finished budget period of 1 at the end of last year. We're currently working with the utilities and with the DOE to get budget period 2 kicked off. So roughly speaking, we're up in this orange area here in central Alaska. Temperatures can get down to -45°C regularly during the winter. So again, challenging place to build. The idea is to use low-cost energy to charge a pump thermal energy storage and avoid running their frame gas turbines, which run on diesel. So very expensive electricity. So this project right now is in that kind of middle of the development stage. We actually, this is out of date. FEED study was on track for the end of last year's completion, so it's complete now. And again, no component showstoppers. We've been working through all of the different modeling cases, and that is near completion now. We're moving on to transient model and control simulations currently. We have 2 other projects that are in early stages, one in Slovakia with VVB as the utility. This is it's a different type of an application. Here they have hydroelectric that, again, they can't curtail simply because they don't have the ability to turn the hydro plant down. So being able to collect that excess power and deliver it at times of higher power prices has a significant value to the utility. We're also looking at an early or late stage discussions to deploy a first pump thermal energy storage project in Africa. That would be back down to a 50 megawatt system. And again, both of these projects are aiming towards 2030 kind of a time frame. This is just kind of an overview, sort of where we've been. We started this effort in 2017, still doing some amount of small scale testing and scaling up of that testing in our laboratory and others. But the initial commercial projects are currently underway. And again, we're targeting to try to get these in the 2029-2030 timeframe. Right, hope that gave you a quick overview of what it is that we have ongoing. Happy to take questions. I think I'm the last speaker, so I'm guessing it will get opened up at this stage. So thank you.
Yeah, thank you very much, Tim. That was an outstanding presentation about your company and the projects that you are involved in. I'm sure that you made the information very accessible to the audience. Thanks for your presentation. And indeed, we can open the floor to questions. I will make possible that you can unmute your mic and you can also switch on your camera. It will take me a minute.
Yeah, I see no questions on the chat. So if you want to ask a question, just raise your hand or just speak up.
I saw a raised hand from Stephen Taylor just a while ago. So if you want to ask a question.
I have a question for Tim.
Yeah, go on.
Yes, sir.
And I was wondering, like, why choose the CO2 as fluid?
No, it's a really good question, because theoretically you could develop a pump thermal energy storage system with almost anything that you could run in a heat pump or heat engine type of a cycle. So ideal gases, air or argon would be possibilities. By using so there's a couple of key characteristics. Number one, we're using a fluid whereby we can actually run this as a Rankine cycle. By reducing the amount of pump work, we can limit the impact that the inefficiency of the pumping process has on the overall round trip efficiency. So that's a key characteristic. The other one is that CO2 has this really nice characteristic where at reasonable temperatures and pressures, we can access the ice water phase transition on the low temperature end, which again makes for a very low cost thermal reservoir. And on the high temperature end, we can work in this 300 to 350 Celsius range, where we can still work with materials that are, again, relatively low cost. You don't have to go to high temperature stainless steels or nickel based alloys. And it allows, again, it's all in the service of trying to come up with an efficient but low cost thermal energy or pump thermal energy storage system.
Oh, good. So for the iced water, you use like it is made iced through a process, or it is supplied because it's in a cold area?
No, that's a really good point. Now we have to design to be able to install this in places, and actually even in Fairbanks, Alaska, I was there in the summer and it was 25, 27 Celsius, so it gets fairly warm. But no, we generate the ice as part of the overall process. So, if you had asked me 5 or 6 years ago when we started this, what was the one thing that I had the least confidence in, that was it. It was, how do you develop an ice generation system that can create thousands of tons of ice every time that you run one of these cycles and do it economically. So we've actually tried several different technologies, and the one we have down selected is this supercooled water ice water slurry generation. Again, if you'd asked me when we started that project about 3 years ago, it was like high risk, high reward. If it works, it's great, but man, I don't know if that's going to actually. It turns out it works really well. And as just a brief aside, we're actually this morning here in Ohio, we actually demonstrated a natural supercooling water event where it was -6 Celsius outside and it was raining liquid water and freezing spontaneously when it hit my windshield on the drive in. So it was a fun day. But yeah, it is the it offers a significant performance benefit being able to run at those conditions, again, so that we can access the liquid phase behavior of CO2. And it's also, as I said, once you find the way to make huge quantities of ice economically, it's a very economical way to do it as well.
Yeah, it's definitely a new and good idea to use iced water.
There were a couple people who didn't think we could pull this one off. So,
Tim, just I'm sorry, I'm picking on you, but since you're mentioning, people wouldn't believe and economically viable, which was the component of the system which was more challenging from a techno-economic point of view? So which is the one that you made the most effort into fitting it, the model?
The compressor. So, without a doubt, that was the one that Well, a couple of things. Number one is, yeah, there are centrifugal compressors that can do what we want to do. Being able to get those to do it in an efficient and cost-effective way was a concern. That's why we launched the axial compressor program with Notre Dame and Cincinnati. The guy at University of Cincinnati was actually a former colleague of mine at GE Aviation, who's a compressor designer, and so he did some really nice work on blade shape optimization. Very successful program. Will that translate into a commercial aspect? We're finding more and more that the centrifugal compressors may end up being a competitive enough solution and they have very limited technical risk. You learn as you do these development programs. And honestly, the other one was this ICE generation. So when we again, this is another case where we went out and solicited DOE funding to do a technology survey, and we looked at 3 different technologies, really 4, but one was before that, on ice water generation, and this is the one that we settled on.
Thank you so much. I see a few raised hands. Andrew Potter, please come forward.
Hiya. It was an interesting talk. I've done some work on the alum cycle and supercritical CO2 at higher temperatures, and this is causing materials degradation problems. I was just a little bit curious as to whether you encounter any materials issues at your lower temperatures.
Yeah, 350 Celsius, it's a pretty well-studied art. There were, going back starting in about 2009, 2010, Oak Ridge National Lab and University of Wisconsin-Madison, and I believe Oregon State did some. I know there was some work in the EU as well on looking at specifically supercritical CO2's interactions with materials. And by and large, if the material was fit for use with steam, it generally speaking would be fit for use with CO2 as well. The exception was 9 chrome steels. There they saw some evidence that there was accelerated corrosion at 500 Celsius, which for steam would be fine, but for CO2, not so much. So yeah, you got to pay attention to it. The challenge with the alum cycle is not only are you working with very high temperatures, 750 Celsius plus, but you also have CO2 with other stuff in it. The CO2 we work with is 99+% pure, no water, whereas the alum cycle, you're looking at residual water, CO, oxygen, maybe even a little hydrogen. So again, Bruce Pint at Oak Ridge did some initial work with that. That does impact those material tests.
Yeah. Okay, thank you.
David, please come forward.
Yeah, thank you, Marco. So I have a couple of questions. One of them is for Isabel, because you mentioned you're working, JRC is working on a report soon to be published about plans, if I got it correctly, plans of DSOs and TSOs to, I guess, specify, design, or maybe report the requirements for energy storage technologies?
Yeah, we have analyzed not only the national plans from member state, but also the distribution and transmission plans, if they have specific policies or measure to support storage. In that sense, we have categorized with green, red, and yellow. If the countries are doing a good job somehow to support the new initiatives for storage, and also making an assessment of the volume of the country, because you can have a lot of power in Germany, but it's not the same that having in I don't know, in Latvia, for instance. So we have normalized the amount of storage expected and also the measures for plans, official national plans, and distribution and transmission plans.
Because in a way, it's a sort of holistic approach to how the grid and the new installations regarding energy storage systems have to come together.
because you can have a country with a lot of support on storage, but if the transmission plan doesn't reflect those initiatives, it doesn't arrive so fast, the measure. So if you can detect the storage in the distribution plan or in the transmission plan, you can have a clearer idea on how the grid evolves in the upcoming years.
Yeah, makes sense. And when is that expected to be published?
Right. We are finalizing details. It was a matter of how to visualize our maps, and I have a colleague working on that. I guess in this month we will be publishing.
Good news. So I'll keep an eye on it. And then, if I may, Marco, I have another question.
Sure.
For Tim now. So Tim, I can see the 3 projects you made reference to are kind of the same scale. So is that just part of a learning process and maybe standardizing the technology, or did you look into minimum scale to make economic sense of the technology?
Yeah, no, that is something that we have spent a fair bit of time looking at. The challenge is, as you go smaller, both cost and performance start to degrade. And so 50 megawatts is about as small as we can imagine things going from an economic perspective. And again, performance, you do get significant performance benefits from, let's say, 20 to 50 megawatts on a turbine. For 50 to 100, you do get a benefit, but it's incrementally smaller. Same thing happens with compressors. Interestingly enough, the compressor is kind of an oddball because efficiency matters, but it matters less than it does for the turbine, because in a heat pump, the objective is to generate heat at a given temperature. So as the isentropic efficiency drops, then you start seeing reductions in the pressure ratio that's required to get to the same temperature. So it's less than a 1-to-1 kind of an impact. Mechanical efficiency, on the other hand, is just a loss. So if you are, again, going to smaller and smaller scales, typically the mechanical efficiencies get to be a bigger and bigger problem. And so that ends up driving the performance of the system more than the isentropic efficiency does. So that's something that, again, from a small scale system perspective, really creates some issues. And of course, Stefano's dealing with this at laboratory scale, right? It's really hard to get, the kind of performance that you know that you're going to get at the larger scales as you go smaller.
Yeah,
So,
exactly. As I mentioned, the scale up is the scale up, let's say, factor in this sense is we hope because again, at the end of the day, even for larger scale machine, we don't have so much validated values. But for example, we are using some surrogate models to transfer our performance curves that has been a little bit more validated to larger scale. And I can confirm that we are targeting something around 0.5, for example, in terms of RTE, sorry.
Yeah. And you'll get there. I mean, just going bigger is key. Marco's smiling. He builds big machines.
I like big machines. Yeah.
Yeah.
I would have a question for Stefano. So the way I understand it, pump thermal kind of capitalizes on the availability of electricity and heat, preferably cheap electricity and heat which is not used. Do you see a particular scenario or a series of application where these would become king, or do you have any, let's say, boundary condition constraint on the application of the technology that you see in the future?
Let's say, generally speaking, what we saw is that in electric market with large volatility of the price, or even better, electric market with negative price, these technologies could have a little bit of I would like to stress a little bit of economic sense in this moment if we look at day ahead only. In that sense, we must think that this type of, let's say, pump thermal energy storage system have to provide the flexibility services and, increase their revenues in this sense. But generally speaking, in my opinion, the best option, particularly for our system that is, as I said, a thermally integrated one, where we valorize also waste heat from industry, is the possibility to work in parallel, having the chance to discharge the thermal energy storage for industrial processes purpose. So in that sense, I can be more flexible in operating my thermal energy storage, and particularly if I have, for example, very close one to the other, negative price charging spots or things like that, had the chance to somehow remunerate in any case my charging period and have a second chance for another charging period. I hope you're getting my point. So the possibility to exploit these systems in a multi-vector dispatchment approach is for sure something that has a sense, in my opinion.
Yeah, while you were talking, I was indeed thinking about more energy vector integration, system integration,
Exactly.
rather than capitalizing on low prices for the sake of reselling energy at a later time.
Yeah,
It is more
exactly.
transferring one type of energy into another one for using it for better, let's say, for a better utilization rate.
Yeah, and obviously in your time horizon, let's imagine 24 hours, 48, 2 days, you can spot a good moment for electricity.
Yeah.
Obviously, this is the best because, it's the more remunerated vector, let's say, at the end of the day, once it is well paid. But, we know the volatility of the electric markets. We know that there are periods along the year where prices are very low, very, very low. So discharging this type of thing without values that are higher than 100 euro per megawatt hour, just to give some rough numbers, is very complex.
Are there any other questions? Yeah.
Yeah, from my side, I would like to ask one question. First of all, good afternoon all, and I apologize for joining late. I just had other colliding meetings, but I'm really very keen to attend this event, even at the last minutes. My name is Abdul Hakim Hasabu. I'm the Dean of Renewable Energy at Cambridge Corporate University, and I also founder and chairman of BET Group America Incorporation, a company established in Delaware. I'm inventor of 3 different technologies. One of them is hybrid photovoltaic thermal, and this is delivering electricity and thermal energy at more than 100 degrees Celsius, up to 130, 150 degrees Celsius. So we integrate this hybrid BVT technology with different coupling scenarios in order to deliver different services. For example, of course, you need to deliver electricity 24 hours per day. Then we couple it with thermal energy storage, and thermal energy storage could be also upgrading the quality of heat we have to run ORC or steam turbine, or hopefully supercritical CO2. So we work on the systems integration level. Our technology is piloted successfully in Germany in cold climates, delivering temperature more than 100 degrees Celsius in winter, and piloted also in Qatar, hot climate, and we're capturing more than 90% of the efficiency. So basically, when you have the power cycle with increasing efficiency, this will have direct impact on downsizing the solar field, and will have positive effect on the economies of the plant. So we work on this PVT together with thermal energy storage, and the power cycle could be ORC, supercritical CO2, or steam turbine, or even combined cycle, and we deliver multiple services. For example, we can get temperature outlet from ORC at 80 to deliver district heating, and then you deliver power and district heating at the same time. So my interest about this supercritical CO2, what I've heard from Tim, that it is also delivering kind of ice as a secondary product, which is very, very interesting for me, because in MENA region, the energy consumption 60 to 80% goes to cooling in summer, like Saudi Arabia, Qatar, and all of these countries. So if we can get this cooling as a secondary byproduct or services, I can utilize it in different ways, not only for cooling, but even for other applications as a systems integrator. So I just need to ask you, Tim, if you have a supercritical technology, what is the minimum temperature for the heat source? And for each megawatt of electricity produced, what is the refrigeration tons you can produce as a side product in terms of cooling capacity or ice?
So I think, yeah, there's a whole lot of questions embedded in there. So when we think about supercritical CO2 systems, there are opportunities to do just straight heat to power conversion. And for those, again, obviously temperature is a critical factor. On the chilling side, the CO2 is, or the ice water slurry generation is not just it's not really a or a byproduct of the pump thermal energy storage system. It is actually the limiting resource in terms of being able to store thermal energy. And the thermodynamicist in me just shudders to say this, but it's the amount of cold that you're storing. So we don't normally consider this as, well, we could also deliver cooling to another site. That said, the supercooled water technology works really well. We've learned a lot about it. CO2 may not be the best refrigeration source for a standalone ice generation system. Ammonia is probably going to outperform it significantly. So it is definitely something that we're interested in continuing to develop as a separate exercise from what we're doing right now. I know we're almost out of time, so I would suggest if you want to just reach out to me via email, I'm sure my email is available there. If not, it's theld@echogen.com. Feel free to reach out and with specific questions, and I can try to do my best to respond to those.
Yeah, definitely. I'll be pleased to communicate via email just to get more information so I can do my integrations for different services and products. And yep. I hope the coordinator of this event gratefully for him to share with us or for her to share with us the contact information of this wonderful group so we can communicate after this event.
Thanks for the questions. I know we are right on the hour. Just one last question for Isabel. So you're monitoring with your platform what is happening in Europe. Where do you see movement? So what do you see coming up as the most invested type of energy storage technology? What it is as an organization you think will happen?
Well, thanks for the question. I can highlight a couple of key movements, I would say. One of them is there is a clear shift from mature technologies like pumped hydro into electrochemical technologies.
Okay.
You see there is a lot of expectations for new facilities of batteries across Europe. And the second one, I could say, a bit more related to the webinar today, there is also a trend to make the facilities bigger. Mm-hmm. So we see a lot of expectations in long duration storage. And in that sense, there are several initiatives to promote the grid scale services and supporting the facilities supporting the grid. There is in the report that we have already published in November, there is some figures about Germany highlighting this shift from batteries for residential purpose mm-hmm. to expectation for supporting the grid.
Okay. Thank you. Thank you. We are overrunning. Yitka, do you want to close?
You're on mute, Yitka. We can't hear you.
Thank you. Yeah, I was just saying that I would like to thank to all the speakers that you made yourself available for this session. I think that it was really very informative, very interesting. Thank you also to the audience that you keep coming, because that really makes us move forward, and we keep coming up with new episodes, and I hope that we will still keep doing that. Also to all the moderators and all the people that are not here on the screen, but they are contributing. And there will be a new session in a few months. We are already working on it, and we will definitely let you know in a due course what it is about when we open registrations. So with this, I think we can call it today. Thank you so much, and we look forward to seeing you next time.
Enjoy the
Thank
weekend.
Thank you.
Goodbye.
Bye.